Hello everyone, my name is Suhantan and I'm from ECE department of VIT Vellore, and I'm going to explain to you the second module in BPHY102L Engineering Physics, EM waves. EM waves or electromagnetic waves are a type of waves that constitute light and are a very important type of waves that are required in communication, like Wi-Fi and radar signals, etc., etc. So the prerequisites for this EM waves chapter is a bit of vector calculus and the Maxwell equations that we learned in 12th standard. So first is in vector calculus, the first thing is we need to know that there are two types of function. One is scalar point function, that is if you input values to the scalar point function, it will give you a value, something like maybe x square plus y square plus z square is a scalar point function, and when you input values in this you get certain results, like maybe 1 comma 1 comma 1 could give you something like 3. That's it. And then now we go to vector functions, which is that yes, you have three different functions but they operate on each axis, and these functions could be same or else different. For example, f bar could be something like f1 I cap plus f2 j cap plus f3 k cap, and if you input values on these, instead of giving you a scalar point, you get a vector, something like maybe you could get something like I plus 2j minus k, something like that. So now the first thing that we need to learn in vector calculus is about the del operator on nub, which is represented by nabla, which transforms this scalar point function into a vector. So how does it do it? So basically the del operator, this is the del operator, and it is nothing but the differential of x in the I direction, that is the I direction or the x direction, differential of y in the j cap or the y direction, and differential of z, that is differentiation with respect to z in the k or else the z direction. And if a scalar point function is multiplied with the del operator, or the del operator operates on the scalar point function, we call it the gradient of phi, which is nothing but the spatial rate of change of this function phi at the direction where it is maximum. This gradient of phi can be also represented as grad phi. And the next operation that we can do with the del operator is by doing the dot product with the vector function f. This is the divergence. Divergence is the closed integral of something like flux over an area, whether on, and this divergence explains how it converges, not how it converges but how much it converges or diverges. And this operation is the divergence of f, and the last one is called the cross product of the del operator with our vector function f, which is known as the curl of f. curl means our vector function f is gonna curl at a certain direction over an axis. This is curl of f, and curl of f can be represented by a matrix, a 3x3 matrix that looks like this. And these are the basic operations that we can do with the del operator. And now let's go to the second order differential equations for our vector calculus that has three identities. The first one is the divergence of curl of any vector function is equal to 0, and the divergence of gradient of any function, of any scalar function phi, is nothing but the del square of phi, which is the Laplacian operator, and finally curl of a vector function is equivalent to the gradient of divergence of that function minus the Laplacian of that function. So this summarizes the differential part. And now let's go to the integral part. We got the divergence theorem, or the Gaussian divergence theorem, which transforms this Gaussian divergence theorem transforms a closed surface integral of any vector function into a volumetric integral of the divergence of that function over a given volume. So let's say that this is a surface through which a flux or something a vector field is being activated, and this is the surface through which, so this is the flux that you could represent, that is the closed integral of ds over this of f bar is equivalent to the volumetric integral of the divergence of the divergence of f over a given volume. This given volume could be something like a sphere or a cylinder or any shape you want to be. And now let's go to the Stokes theorem or the curl theorem. It states that the line integral of our vector function f is equivalent to the closed surface integral of the curl of our function f. So we have a function f that's acting on this line. Let's say this is dl. This is dl for us, and this is this closed integral over the whole wire through which our vector field function is acting is equivalent to the surface integral through which the curl of our vector field function will act. So this summarizes the vector calculus that's required for EM waves. Now let's go to the four main equations. The four main equations can be written as First is the Gauss law for electrostatics, which is the closed integral of E bar dot ds bar is equal to q enclosed by epsilon naught. The Gauss law for magnetics, which is d bar dot ds bar, which is equal to 0 since magnetic monopoles don't exist. And then we have Faraday's laws of induction, which is E bar dot dl bar, or the line integral of electric field over a wire is equal to minus of n d phi b by dt. Here d phi b is the magnetic flux over a certain system like a solenoid or toroid with a certain amount of turns n. And finally we got the linear integral, the line integral of b dot dl, which is the Ampere circuital law, which states mu naught I, or the amount of current that goes through a conductor will produce a magnetic field surrounding it. For instance, a straight conductor would have magnetic fields in circles. And these are the 4 equations that we are going to deal with. So the first equation is the Gauss law of electrostatics. And the first thing that we can do is apply the divergence theorem to this. So upon applying divergence theorem, it becomes the divergence of electric field over a certain volume, and we can write q enclosed to be the volume charge density times a certain volume. We can also write this to be another volume integral that is similar to this volume integral, so that we can equalize them. This equalization is a must because that's how we will get the first differential form of our first Maxwell equation, that is divergence of electric field is equivalent to the volume charge density divided by the permittivity of free space. And now let's go to the second equation, which is similar to the first equation, will look like this, but instead of rho by E, you get rho by epsilon naught, you get 0. This is because no magnetic monopoles exist and that magnetic fields are closed loops. They form in closed loops. So now let's go to the third equation. So the line integral of E dot dl is equal to minus n d phi b by dt. So this is for a solenoid of number of turns to be n, but we can take this number of turns to be 1, just a single ring, so that it's much more simpler. So E dot dl is equal to minus d phi b by dt, and we know that phi b can be actually written as a closed integral of b bar dot da bar or ds bar. And since this is an integration over space and b is a multivariable function which depends on both space and time, and this is only over space, we can actually bring this differentiation into the integration, and this won't change the integration like before, because usually The only time where the integration and differentiation would cancel out is when you have something like d by df by dx and integration, and this one whole integrated over dx. This is where the integration and differentiation would cancel, but over here nothing happens. So this would just get turned into line integral of e bar dot dl bar is equal to minus of line integral of this. And now is where the fun part. We use the Stokes theorem and we get this. The curl of E, that is the closed integral of curl of E, is equivalent to minus of the closed integral of dou B by dou T. And since we are integrating over the same variables, that is the same area, we can cancel them out, and hence we get the third equation, which is minus dou B by dou T. So now let's go for the fourth equation, which is the Amperian circuital law. Line integral of B dot dl is equal to mu naught I, and over here I can be written as current density times area, and we know already that this can be written as the closed integral of current density over this. We already know the drill. So we use Stokes theorem once again and we arrive at this. So if you don't know how this came, it's just that we get the curl of B, get the closed integral of curl of B is equivalent to the closed integral of J over A. And since we are integrating over the same limits, we can cancel it and we get this. So these are the four equations that we are gonna deal with. But I'm gonna be more interested on these, the third equation and the fourth equation, because why? We're going to apply the second order identity, that is the first identity, that is divergence of curl of a vector function is 0. So let's do it. So first let's apply the divergence of curl of E. So if I do that, then I should also do divergence of dou B by dou T. And since this is a time derivative and this is a space derivative, I can take the space derivative inside and it's not gonna change, because if you don't know, then dou square of dou xy of a function is equal to dou square of dou yx, where this one is differentiated first by y and then by x, and this is differentiated first by x and then by y. These are equal, so I can just switch it. This means that this will give me the divergence of curl of E is equal to minus dou by dou T of divergence of B. And since we know from the second equation divergence of B is 0, this one is 0, which means the Faraday's laws of induction actually doesn't give any contradiction. Now let's apply this to Ampere's circuital law. So if I do this to Ampere circuital law, we find out that mu naught of divergence of J. So the question is this actually 0? In case of magnetostatics, that you would have been taught in the 4th chapter of 12, this one is taken to be 0. But in electrodynamics, like current electricity, this is not 0, which means that this contradicts the fact that this should be 0, because this is an identity that has been proved. And if this is not 0, then we should add something so that it should become 0. So for that, let's get straight to work by defining what is current density. So current density is nothing but we take a section of this, cross section of this conductor, and then we see that electrons flow like this from one position to another, and this is the area through which it flows. So I is equal to the the closed integral of J dot ds. But we also see that the charges in this conductor are exiting in the sense that you can say that there is a negative, or you could say a loss in the volume charge density, which means that it is nothing but the loss in volume charge density, and for context, I is nothing but Q by T, and we can also write it to be dou Q by dou T. Yes, and Q from our old thing, we can write it to be the volume integral of dou rho by dou T over a volume like this. This cross section has a volume. So now that we know that there is a loss in charge, we can just put a minus symbol, and now we just have to equate this and this. So it's nothing but equal to J dot ds is equal to minus of dou rho by dou T over the volume. And we can use the Gauss divergence theorem for the 3rd time. Yes, it is very useful. Get that the dot product of J over the volume is equal to minus dou rho by dou T over the same volume. And this is important because see, this gives us that the dot product of the current density plus this change of volume charge density is equal to 0. This means that this is the continuity equation, or this is the correction factor that is important for our this is the correction factor that is important for us. So yeah, this is known as the continuity equation, and this is the correction factor. So now what we can do is, this is nothing but the displacement current topic that was poorly explained in 12th standard, and in some parts it was just deleted. So yeah, so now we can just bring this to the other side. So it would just be dou rho minus dou rho by dou T we can implement the first equation, that is, yes, this one over here. It is nothing but the divergence of J is nothing but minus the divergence of E over this multiplied by epsilon naught. It is multiplied by epsilon naught, and we can just take the divergence outside, as I said, from over here. So it is that this correction factor is nothing but minus epsilon naught times the time derivative of the electric field. So finally we can write the four Maxwell equations. The first equation is the divergence of electric field to be equivalent to the volume charge density by the relative permittivity, also known as the Gauss law of electrostatics. The divergence of magnetic field is 0 because of no magnetic monopoles, the Gauss law for magnetics. The curl of E is equivalent to the negative rate of change of magnetic field with respect to time, the Faraday's law of induction. And finally, the curl of B is nothing but the relative permittivity, the permittivity of free space. I mean, I might have said relative permittivity for here as well. This is permittivity of free space, and this is permeability of free space multiplied by the current density plus epsilon naught times the rate of change of electric field with respect to time. This is the Ampere-Maxwell law and not Ampere-Circuital law. This is because this law, the first Ampere-Circuital law, this one only holds for DC currents, or DC in the sense that only for steady currents, that is, they don't have that much of voltage fluctuations and this and that. It's like 5 volt is only 5 volt from like t time of 0 to time of infinity or whatever. But this one can be also done for AC currents as well, or anything. And this one fails for AC currents because it lacks this term. And yes, so from this we can now derive the electromagnetic wave equation by doing one last twig, and that twig is the third equation. We are gonna curl these two, either of these two. So first I will curl this, because we are gonna try to find in terms of electric field. So first I will curl this. So if I curl it, I will get curl of E is equal to minus dou by dou t curl of B. So now let's start the math. So this would be nothing but gradient of divergence of E minus the Laplacian of E, which is equal to minus dou by dou t of mu naught J plus mu naught epsilon naught dou E by dou t. And now let's take the minus terms to the other side, so they become plus. So we get Laplacian of E is equivalent to the gradient of rho by epsilon naught plus the differentiation of mu naught j with respect to time plus mu naught epsilon naught of the second order differentiation of electric field with respect to time. So here we are gonna say that this is the wave equation that would be if we are considering it from the source. That is, this is the source and this will have some electric field and some magnetic field as well, some rho and some j. That is, keep in mind that close to source rho and j are non-zero. But let's talk about free space. At free space, rho and j are 0, meaning that these two terms will become 0. And this gives us a very neat wave equation that looks like this. And from waves and oscillations, we know that del square the Laplacian u by 1 by v square of the dou square u by dou t square, this transverse wave equation matches with the EM wave equation, and this means that this is equal to 1 by something, and this something is nothing but the speed of light, which is nothing but 1 by root of mu naught by epsilon naught. And the speed of light is 299,792,458 meter per second, or around 3 into 10 power 8 meter per second. And that's it. And this marks the end of EM waves. And we can do the same curl with B as well, and which I will do it now. So curl of B is equal to curl mu naught of curl of J plus epsilon naught of curl of E, that is this one. So this one is simple. This is nothing but the divergence of B minus the Laplacian of B is equal to mu naught times curl of J, plus we can substitute the third, that is Faraday's law of induction over here, which would speed things up by giving us minus mu naught epsilon naught of dou square B by dou t square. And since we are talking about free space and we already have this to be 0 from the Gauss law of magnetics, since we are talking about free space, this one will become 0 and this one is already 0, meaning that we will get easily this. This means that for both electric and magnetic field, the equation stands. And a cool feature about this EM wave is that if I take this to be axis, to be the transversing axis, and that if I take this to be the z axis through which it's gonna transverse, and then on the y axis if I take the magnetic field, it would go something like this. But the really cool part is that that the other one, that is the electric field, will be perpendicular to it and moves through the x-axis and goes like this. And this is a cool feature of the electromagnetic wave where one of them is perpendicular to the other, and that summarizes the electromagnetic waves. And there are different types of electromagnetic waves like IR, UV, visible light, X-rays, gamma rays, microwave radiation, radio waves like AM and FM, and that's it. And this summarizes the very poorly explained topic of 12th and one of the most beautiful topics of engineering physics. And this is TM Swanthan concluding. Thank you.